Now we're going to look at what are called divide and conquer recurrences or recurrence relationships. So these all have this form or something similar to this. So in this case, m would be an integer. And so for what we're going to look at, we're actually going to assume that b is 2, or all of our examples will use b equals 2. But you're not technically limited by that. So that means we'll have things of this form. So why require that n be a power of 2? Well, if we're going to keep dividing things by 2, we want to keep getting integers each time. And so if I had n was 8, 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1. Will get us back to our basis condition. Now in reality, you could have values that where n wouldn't be a power of 2, like n was 9 or n was 10 or whatever. But in terms of analysis, you may make these assumptions to make the math easier, right? Now these types of recurrences show up a lot in data structures and algorithms, because there's lots of algorithms that use a divide and conquer approach, and so they can be described in terms of this. By divide and conquer, what that means is you take the values, so let's say you have all these values. Maybe you basically can divide these into 2 sets, and then you maybe focus on this set, which is approximately half of the total, and you divide it into 2 parts, and maybe now you focus on this half, and you divide it into 2 parts, and so forth. So each time you're basically trimming out approximately half of what you had before, and that's where these occur. So let's think about what's going to happen in terms of what the next value is. Before, we had things like this. And maybe we had a multiplier, maybe we had a constant. But to keep it simple, we'd have something like this. And we'd say, okay, well then, s of 1 was equal to something. S of 2, because of this relationship, was equal to s of 1. S of 3 was equal to s of 2, and so forth. If our relationship is now something of this form, and we have a starting value of s of 1, well then if we're using s of 1 over here, what is this? Well, this would be s of 2, right? Because we have s of 2 divided by 2, where the top 2 is this 2, this right here, is equal to s of 1. But then if we're using s of 2 here, what is this value? Well, it's going to be s of 4, because s of 4 divided by 2 will be s of 2, right? 4 divided by 2 is 2. And that means if we have s of 4 here, then this is s of 8. We'll work it that way. So we won't work with s of 3, s of 5, whatever. This is where we're making use of this relationship and using powers of 2. And once again, that doesn't entirely match up with reality, but its purpose is to make the math easier to try to understand, because when we're analyzing algorithms, we're basically trying to put a bounds on something and trying to get an idea of how things grow or change. Before we look at examples though, let's look at a couple of special cases of geometric series. Okay, so recall that our general formula for the geometric series, or at least the way I prefer to write it, would be a times r to the 0 power. Normally, since r to the 0 is 1, you just say a, but plus a to the r to the first power, plus a times r to the second power, plus dot dot dot, plus a times r to the n minus 1 power. I prefer to write it this way because now we have n terms, which goes along with many of the problems I'm solving. But if you stop this at r to the n minus 1 power, then the closed form solution of this is a times r to the nth power minus 1 and r minus 1 down here. So one special case would be a equal 1 and r equals 2, and then you'd have this 1 plus 2 plus 2 squared plus dot 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 plus 2 to the nth power. Now I have n plus 1 terms technically, has the closed form solution of 2 to the nth plus 1 power minus 1. You take this formula, plug in this a, this r, and it simplifies to this. We can also have a equals 1, r equals 2, but we write it like this, 1 plus 2 squared plus dot 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 plus 2 to the log n minus 1 power, where log n would be some integer. So maybe this reduces, if this is log base 2, so for example, if I have log of 2 of 8, that gives me 3, right? Because 2 to the third power would be equal 8. So this right here, so I wrote my spot here, would be 2 to the log n and then subtract 1 power. Or excuse me, subtract 1 from that. So this would be the closed form solution. That's a closed form solution for this one. And finally, you might have this. A is equal to 1, r is equal to 1/2. This shows up sometimes when analyzing algorithms. So this would be 1 plus 1/2 plus 1/2 squared, which would really be 1/4, plus dot dot dot, plus 1 over 2 to the nth power, because 1 to the nth power is just 1, will be 2 minus 1 over 2 to the nth power. That's a closed form solution for that. All right? So some of these may show up in some examples, so let's work an example or two. S of 1 is equal to 3. S of n is equal to S of n divided by 2 plus 4. That begins when n is greater than or equal to 2. And we'll assume n is equal to 2 to the nth power, where m is an int, or integer. Right. So if we use what's called the substitution method, or what I've been calling the expand, guess, and verify method, we have S of n is equal to S of n divided by 2 plus 4, which is equal to what? Well, this right here is replaced by an S of n divided by 4 term. So it'll be S n divided by 4 plus my original 4, right? And this becomes S of n divided by 4 plus 2 times 4, which is equal to S of n divided by 8 plus 4 plus our 2 times 4 is equal to S of n divided by 8 plus 3 times 4, dot, dot, dot. And I'm trying to find a pattern here, as always. So what do we have? Well, let's rewrite this right here, this first one, as S of n divided by 2 to the first power plus 1 times 4. Right? Is that still the same thing? Sure. 2 is equal to the first power. 4 is equal to 1 times 4. So this right here then is S of n divided by 2 squared plus 2 times 4. This right here is equal to S of n divided by 2 cubed plus 3 times 4. So now I can see a power of 1, I have a 1. Power of 2, I have a 2. Power of 3, I have a 3. So I work my way down, I can see I have something of this form. S of n divided by 2 to the kth power plus k times 4, and I'll just write 4k. Now eventually, this right here reduces to our base condition, S1. So eventually, n divided by 2 to the kth power is equal to 1, which means we have n is equal to the kth power, And if I do log base 2 of both sides, then I get this, that k is equal to log of n, where it's going to be log base 2. All right? So that means we have s of n is equal to s of 1 plus 4 times k, which we said is log base 2 of n. And s of 1 was 3, so we have 3 plus 4 log base 2 of n. And that's our guess for a closed form solution. So just like before, we want to use mathematical induction to verify this. All right. So we have the basis, and that says s of 1 is equal to 3. We were given that. We want to use the formula to try to confirm that. S of 1 is equal to 3 plus 4 log of 1. This is log base 2, which is equal to 3 plus 2 to the 0th power gives me 1. So 4 times 0 is still just 0. So it becomes 3, and it matches what we're supposed to have. We assume that s of k is equal to 3 plus 4 times log of k. That's log base 2. All right. And so now what do we use for the next term? Well, remember we're using the next term. When we had something of the form s of m is equal to s of n minus 1, then when we had s of k, then the next term was k plus 1. But what's the term that comes after s of k for this recurrence relationship? Well, it'll be s of 2k. Because if I divide this by 2, right, take n, divide it by 2, 2k divided by 2 would be s of k. So this will be equal to s of k plus 4 using our recurrence relationship. Now we substitute our assumption into this to get 3 plus 4 log of k plus 4, which is equal to 7 plus 4 log base 2 of k. Now we want to see if our formula will produce the same thing. So s of 2k will be equal to 3 plus 4 times log base 2 of 2k, which is equal to 3 plus 4 times log of 2 plus log of k. Right, we can take this and expand it, which is equal to 3 plus 4 log of 2 plus 4 log of k. And log of 2, since this is the base is 2, 2 to the first power is equal to 2. So this becomes 3 plus 4 log of k, which is 7 plus 4 log of k. The same thing we had here. So it does work. And if you wanted to, if you still weren't sure, and I will do this sometimes when I'm testing things out, is I will just plug in several values. So I would produce, say, the first 3 or 4 values using the recurrence relationship, use my closed form solution, see if I can get the same thing, and test it out that way. But that's not technically a proof. This is the proof. All right. Let's do another one. S of 1 is equal to 5. And we'll say s of n is equal to 2 times s of n divided by 2 plus 3, where n is greater than or equal to 2, and n is equal to 2 to the nth power, where m is an int. Now this 2 and this 2 are really two different things. Okay, so they don't have to match. Just like we saw in the previous example, the multiplier was 1. And it is possible to have something like s of n is equal to 3 times s of n divided by 2 plus something. Okay, so they don't have to be the same. Use the substitution method. S of n is equal to s of n divided by 2 plus 3, which is equal to 2 times s of n divided by 4 plus 3, which is equal to 2 squared plus, or excuse me, 2 squared times s of n divided by, and I'm going to go ahead and write 4 as 2 squared, right? Plus 2 times 3 plus a 3. So this 2 is multiplied by the 3, and then we already had a 3. Now this becomes 2 squared times 2 times s to the n divided by 8 plus 3 plus what we had before, 2 times 3 plus 3. Just like I said in some other videos, I don't want to simplify this too early because I'm looking for a pattern. And so this right here becomes 2 cubed s of n divided by 2 cubed plus 2 squared times 3 plus 2 times 3 plus 3 dot 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 equals, it looks like I have this 2 to the kth power times s of n divided by 2 to the kth power plus, there's a 3, there's a 3, there's a 3, but what changes for each of these 3's is what power of 2 I multiply by. This is 2 squared to the first to the 0 power. But notice here I have, this is 3, but I start here at 2. When this is 2, I start here at 1. So this becomes 3 times 2 to the k minus 1 power plus dot 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 plus 2 to the first power plus 2 to the 0 power. And this is a geometric series. And in fact, this is one of those special cases we saw earlier. So this right here becomes 2 to the kth power times s of n divided by 2 to the kth power plus 3 times 2 to the kth power minus 1. That's a special case, except here a in our geometric series was 3 instead of 1. So eventually this right here becomes 1, and so we get s of n is equal 2 to the log of n, for the same reason we had before. We take this right here, eventually works its way down to 1, we do this manipulations, and we get k is equal to log of n, log base 2 actually, times s of 1 plus 3 times 2 log of n minus 1. And so this is equal to s of 1 is 5, so 5 times 2 log of n plus 3 times log of n minus 3. So s of n is equal to what? Well, what is 2 to the log of log base 2 of n? Well, this power here says 2 to some power is equal to n. And so we'd replace this by whatever that power is. Well, we're raising 2 to that power. So this right here actually reduces just to n. So we have 5 times n. So this is 5n. Same thing for this, plus 3n minus 3, which is equal to 8n minus 3. That's our guess for a closed form solution. Right? So let's test that out. So we'll verify this. So our basis is that s of 1 is equal to 5. We assume that s of k is equal to 8k minus 3. That's using our closed form solution we just produced. And now s of 2k is equal to 2 times s of k plus 3. That comes from this right here. And now we replace this with our assumption. So this is 2 times 8k minus 3 plus 3. This 3 right here becomes this, which equals 16k minus 6 plus 3, which equals 16k minus 3. And so now over here we want to check these. So this would be s of 1 is equal to 8 times 1 minus 3, which is equal to 8 minus 3, which is equal to 5. That's what we have right here. Now s of 2k will be equal to 8 times 2k minus 3, which is equal to 16k minus 3. Those are the same. Just as a little check, let's put in some values. So if we iterate using the recurrence relationship, we have s of 1 was equal to 5, s of 2 was equal to 2 times s of 1 plus 3, which is 13. S of 4 is equal to 2 times s of 2 plus 3, which is equal to 29. And we'll stop here. S of 8 is equal to 2 times s of 4 plus 3, which is 61. Okay, what does the closed form solution say? S of 8 is equal to 8 times 8 minus 3, which is 64 minus 3, which is 61. Same thing like it should be. So there is how we can use the substitution method or expand, guess, and verify method to solve some divide and conquer recurrences. In my next video, we'll see the recursion tree method to solve one of these same problems.